Today's daily code video of the day is count the number of fair pairs, number 2563. For this problem, we're given a zero index integer array nums of size n and two integers, lower and upper. We want to return the number of fair pairs. So a pair of I and j is fair if 0 is less than or equal to I, which is less than j, which is less than n. And lower is less than or equal to nums of I plus nums of j, which is also less than upper. So we need a pair of numbers that is going to be greater than our lower value, less than our upper value, and I and j need to be within our array. So for this problem, we are going to use sorting and binary search to solve the problem. So in example 1, there are 6 fair pairs. We have 0 and 3, 0 and 4, 0 and 5, 1 and 3, 1 and 4, 1 and 5. And that all satisfies our lower is 3 and our upper is 6. So the smallest value we can make is 3, the largest value we can make is 6, and those are all the combinations that make those two, all the values within those two values. So let's first simplify our problem. If we're going to check every possible pair I and j in the array, we'd end up with a time complexity of O of n squared, because we would need to check each number twice, which is extremely inefficient for large arrays. We can instead simplify and optimize our solution by first sorting. So we're going to use a sorting algorithm, which gives us the ability to use binary search to quickly find the range of values that form the valid pairs within a given element. So for our binary search, we'll use a custom lower bound function to first find the element that is not less than our given target value. So let's go ahead and dive into the code real quick, and I'll walk you guys through it. So it's important to take note that our return value is a long. So we're going to be dealing with very large values here. So we are going to first initiate a private function. It's going to be outside of our count fair pairs function. So we're going to have a private, it's going to return longs, and it's going to be our lower bound helper function. It's going to receive an integer array, an integer low, an integer high, and an integer element. So the goal of this lower bound function is simply going to be a custom implementation of our lower bound value. It returns the index of the first element in our number array that is not less than our element, the value element. So it works by using binary search to narrow down the range until our low gives us the position of our desired element. To make this easier to understand, we can first define our count fair pairs function. So we're going to have arrays.sort nums, just makes it easy to sort our numbers array. And then we're going to identify a long called answer, which we're going to use to calculate our answer, of course. So we're going to have a for loop. For int I, it's going to be equal to 0 as long as I is less than nums.length. I is going to increment. We are going to first assume that we have picked nums of I as our first pair element. So we're assuming nums of I is our first pair element. So low is going to indicate the index of the first element with the sum is greater than or equal to lower. So long low is going to be equal to our lower bound, and then we're going to pass it the elements. So it's going to receive nums I plus 1, because that is 1 greater than our low value. It's going to receive nums dot length minus 1, because that's our high value. And for our element, we're going to return lower minus nums of I into the function. So what is that doing? We are going to find the smallest index low where nums of I plus nums of low is at least the lower value. So that in our binary search function, we're going to use these elements to make sure that the smallest low value, or our long low, variable, is going to be as close to our lower variable as we can get. We're also going to do the same thing for our high value. So long high is going to be equal to our lower bound. We're going to pass it nums I plus 1, nums.length minus 1, and we're going to pass it upper minus nums of I, but we're also going to do plus 1 for this one. So we're trying to find the closest number to our upper bound. We can then update our answer, so our answer is going to plus equal high minus low. So this answer plus equals high minus low kind of simplifies and shows you how this is exactly going to work. We are going to find the closest number to low possible and the closest number to high possible, and then we're going to use those two as a pair. So all the numbers within those two numbers is also going to be part of a pair. So let's go ahead and define our lower bound function so we can see exactly what's going on in here. We're going to have a while loop, and while our low is less than or equal to our high, this is a very simple binary search. We're going to have an integer middle. It's going to be equal to our low plus our high minus our low divided by 2. The reason we use the low plus high minus low divided by 2 is simply because of we're going to be dealing with very large numbers here, and by using this function instead of, let's say, low plus high divided by 2, it keeps the elements within a reasonable range and allows us to manipulate these numbers. So after we identify our midpoint, we're going to check if our nums of mid is greater than or equal to element. So element in our low case is lower minus nums of I. Low element in our uppercase is upper minus nums of I plus 1. So as long as nums of mid is greater than or equal to our element, high is going to be equal to mid minus 1. Otherwise, low is going to be equal to mid plus 1. So we're going to be updating our mid value. And after this while loop breaks, we can return our low value. So that is our binary search, and that is our function. So, just going over it again, our lower bound function is a custom implementation of our lower bound. It returns the index of our first element in nums that is not less than element. So we use binary search to narrow down the range until low gives us the position of our desired element. In our count fair pairs function, we start by sorting our array, and then we're going to iterate through each element of the array once and assume that nums of I is the first element in our pair. So for each number, we're assuming we're pairing it with nums of I. So we're pairing nums of I, and we're going to find whichever other element in the array works to pair with nums of I. So finding a valid pair is going to be done in ranges. So we're going to use a lower bound twice by checking the smallest index and the highest index. So we're checking nums of I plus nums of low, and we're checking nums of I plus nums of high, and we're seeing if it exceeds our upper or is below our lower. So that's it. If we run this, passes our test cases, and if we submit it, it passes all solutions with should be O of n log n time complexity. Thank you, and follow for more daily LeetCode solutions.